Hello guys, welcome back to my channel. Today I am going to cover day 5 of phase 2 about robotics. So let's start with the point that you must have built the URDF and configured the kinematics. The maths check out on a paper, but when you launch the simulation, the model refuses to walk by itself. Gazebo is a black box physics engine. It handles gravity and collision, but it contains no native logic for coordinating 8 independent joints into a functional gate. Most developers fall into the ROS2 control trap, sending joints commands from an external node at 50 Hz. Network overhead and communication jitter introduce significant latency between your controller and simulation state. This creates a puppet architecture where the robot reacts to the delayed instructions. To achieve stable movement, you must bypass the ROS to messaging layer entirely and treat the robot as an integrated agent. Gazebo plugins provide the necessary interface. These are C classes that run within the simulator's own process, providing direct access to the physics and sensor data. Quadruped locomotion is rarely just like a kinematics problem. It is systems architecture problem that requires synchronous execution. To eliminate latency, you work with the Gazebo's internal clock. The physics engine advance in a 0.001 second steps or 1000 Hz. In step 1, the simulator calls the plugin update function. Here you read the sensors, compute the state machine, and calculate torques. In step 2, the physics engine advances 1 millisecond. It takes the computed force, applies them to joint, and resolves terrain collision. Finally, the simulator updates sensor readings and publishes data back to roster. Then the cycle repeats immediately because your C code executes in step 1 before the physics engine moves. You are effectively operating with zero latency related to the simulation state. This 1000 Hz lock step avoids the jitter of asynchronous ROS2 message which arrive at a random interval and the simulator resolves the next frame of reality. Building an aware quadruped requires dividing the workload across a hierarchy of specialized. World plugin monitors the entire environment, tracking global parameters like terrain friction across the simulation scene. Sensor plugin handle individual devices processing a low-level data like applying complementary filters to an IMU. Finally, model plugins act as the primary gate controller scoped specifically to the robot's joint for a quadruped gate control. You will spend most of your development time engineering allows the gate logic to respond to changing ground condition from the world plugin while receiving filtered orientation data from the sensor plugin. To integrate your logic, the code C code follows a specific life cycle beginning by inheriting from a parent model plugin class. The first essential block is the load method, which the simulator executes once upon startup. During load, the plugin initiates join references, allowing the code to directly manipulate the robot's degree of freedom in a memory. While initializing, the script also sets up event listener. This listener registers your code to trigger every time the simulator prepares to advance its physics. This listener points to the update method. This is where your high frequency gate logic and phase transition run 1000 times per second. Without this specific macro, Gazebo will completely fail to recognize the compiled library file when it attempts to load your model. Load, bind, update, and register. This C lifecycle ensures your logic is correctly embedded within the simulator's execution thread. We can see the advantage of a synchronous access by looking at how a plugin movement a foot hits the terrain. The physics engine provides normal force, representing the pressure the leg exerts downward against the surface. It also provides tangential force, the lateral push the leg generates as it tries to move forward. If the tangential force exceeds a normal force multiplied by the friction coefficient, then foot is slipping. This calculation relies on the world plugin providing a real-time friction values for the specific ground surface the robot is standing on. Resolving this logic in step 1 before step 2 moves the joint, let the gate controller instantly adjust the leg's motion to prevent a fall. An external ROS2 controller would only even receive the slip data from after the robot's balance had already been fatally compromised. This architecture does not replace ROS2, it reassigns it. ROS2 remains the ideal tool for high-level path planning and navigation. While ROS2 decides where the robot should go, the model plugin manages the low-level coordination required to execute those commands safely. The plugin receives the low-frequency velocity targets and smooths them into a high-frequency joint commands, eliminating jitter. To implement this, you should follow a systematic testing workflow. First, develop the trotting gate plugin and tune the proportional gains until the stance phase is stable. Once the basic gate is reliable, instrument the system with sensor plugin to fuse orientation data and world plugin to simulate variable terrain conditions. Standard simulation usually treats the robot as a recipient of delayed commands. Implementing these plugins shift that control in the simulator's own timeline, allowing the controller to maintain balance even at context condition shift.